Now we're going to talk briefly about other methods for solving circuits. You do not need to learn how to use any of these methods that are equivalent to nodal analysis, but it's good to know they exist in the world in case somebody else you meet at your job in the future is using a different method than you to get to the same final answers. So one method, which is kind of the dual of node voltage method, is called mesh current method. So with node voltage method, if you remember, we labeled unknown nodes, specifically their voltages, and then we applied KCL at the node intersection. So we're going to do kind of the exact opposite. Oops. We're going to do the exact opposite for mesh current method. So here we're going to label mesh currents, which are these little current loop arrows drawn here. So they don't represent necessarily actual current, because in the case of I1, look at it's I1 minus I2 the other direction. So it's not like I1 is the current through R3. It's kind of a combo of these mesh currents. So after you label the mesh currents, then you'll apply KVL instead around each loop. And then just like we needed supernodes to be able to solve for circuits that have voltage sources in them sometimes, there are cases in mesh current method where you're going to need to do something similar when there are current sources in the system. And I think that's really all I want to show you for this method, but do notice that they end up with equations relating these mesh currents instead of relating nodal voltages. That's the kind of differences. They're going to end up with a bunch of currents and you're ending up with a bunch of voltages. But we can use Ohm's law to always get the other in our circuit. The other method I want you to be aware of is kind of an ad hoc combination of KVL, KCL, and Ohm's law. This is how Professor First teaches it in the intro course. It doesn't require, I would say it's easier to implement in the sense that you're only using KCL, KVL, and Ohm's law over and over and over again, which is what you learned in Unit 1. But the downside is that it requires a larger system of equations. So let's work through how you would do this ad hoc method for the circuit here on the screen. So first we'll label the current through each resistor. I'm just kind of choosing a direction right now. And then this I5, we actually know in this case, that would be negative 20 milliamps because it's in series with the 20 milliamp source, but pointing in the other direction. Okay, and so then I can write a KCL here and here essentially. So for this first one, I have I1 is equal to I2 plus I3, and for this one I have I3 coming in and I4 minus 20 milliamps coming out. Okay, so I have 4 unknowns right now, which means I'm going to need 4 equations. Now let's compare that with node voltage method, right? If I'm doing node voltage method, I'll do that in purple. Ground, here's 10 volts, here's V1, here's V2, and then this one right here, since I know this is negative 20, I can immediately use Ohm's law to calculate this one. So this is an actual known voltage. So I have 2 unknowns. So I guess you could say this one here is, since the current is technically flowing 20 milliamps this way, this is going to be a higher voltage here than this one. So V known is going to be V2 plus 20 milliamps times 3 kiloohms. Okay. Back to our ad hoc method though. So how are we going to get our other two equations now? So yeah, we need 4 equations in the ad hoc method and only 2 in the node voltage method. So we need 2 more equations now. And so we'll get those by doing KVL loops. Zoop, zoop. The only problem is, just like mesh current, you can't do KVL loops with this current source because we don't know the voltage across the current source. It could be anything. So we'll just do these left 2 loops, but that should be sufficient because that'll give us 2 more equations. So in the case of this left one, if I start here, I'll look at the sign where I come out. I get 10 volts minus whatever the voltage is across V1 minus whatever the voltage is, right? Because this is V1. Over here is in this direction of the arrow V2. So minus V2 better be equal to 0 by KVL. So these ones were KCL. These ones were KVL. And then over here, let's see, for the second loop, I have plus V2 minus V3 minus V4 equals 0. And then finally, I will replace the currents, or sorry, the voltages in these last 2 expressions using Ohm's law, because with Ohm's law we know V is equal to IR. So in this case, V1 is equal to I1 times 1 kiloohm. V2 is equal to I2 times 4 kiloohms. So minus 10 equals 0. And then for this equation, V2 is I2 times 4 kiloohms. V3 is over here. So it's going to be I3 times 2 kiloohms. And then V4 is I4 times 5 kiloohms. And all that's equal to 0. So now I have, let's highlight them. I have 1, 2, 3, 4 equations with 4 unknowns, I1, I2, I3, I4. So that's a system I could solve and then get all those currents. Okay, so we've learned over this whole class a number of ways to solve for circuits. In Unit 2, we learned how to simplify circuits using equivalent resistance. We learned about current and voltage dividers also in Unit 2. And then in Unit 1, we had learned about using KVL or KCL like a single time in Ohm's law to solve for unknowns in a circuit. And then I just showed you a way to use those kind of systematically to do any circuit. And then we learned all of Unit 3 now. We've been working on nodal analysis or node voltage method. Just gonna have 2 names for that. And we briefly learned that there's something called mesh current, which is kind of the dual of node voltage method. And then finally, you're going to learn one more way of doing this next term in 1230 called superposition. So there's many ways to solve a circuit, but some ways may be easier or harder in certain situations. So let's take a look at that. Which method would you use in each situation? After I show you each screen, I want you to pause the video for a few seconds and think about which of the methods you would use to solve that specific circuit. And then you can unpause the video once you have an answer, and I will tell you what I think in comparison. Okay, so which method would you use to solve this circuit and why? Okay, so when I look at this, I see just a single source. So when I have a single source, I often think to myself, I probably don't need node voltage method. I might be able to combine resistors. Let me see, are there resistors in parallel and series I can combine? Well, here are 2 in parallel, 2 in parallel, 2 in parallel, 2 in parallel. That seems like a great approach then. I'm going to simplify that way and solve for current by doing equivalent resistance and simplifying my circuit. Okay, how about for this circuit? What would you do to solve this circuit, and why would you choose that method? Okay, so this actually looks very similar, I think, to some of the ones we did this unit for node voltage method. So yeah, I have two sources, which immediately kind of indicates to me that I might need to use something like node voltage method. And the nice thing about node voltage method is there's only, if I make this ground, this is 9 volts at this node, this is 12 volts at this node, I only have a single unknown nodal voltage. So that's going to be relatively straightforward for me to solve algebraically, and I don't have to solve a whole system of equations. So I would use nodal analysis on this one. Okay, how about this circuit? Okay, with all these multiple sources, we might think we want to use node voltage method again. But there's so many voltage sources in this case, I actually know all the nodal voltages. So this, if I label this ground, I know this is 16, I know this one's 12, then I know, tracing through this way, that this one's 12 minus 8, which is 4 volts. So if I know every node voltage in the circuit, then I don't need to apply node voltage method or nodal analysis. And in this case, I can just apply Ohm's law and or KVL, or using like node voltage differences here to get this current. So I would say this is the approach I'm using, because I know that 16 minus 4 tells me that the voltage across this resistor is 12 volts, and then I can apply Ohm's law. Okay, and finally, what method would you use to solve this circuit and why? You might think, oh, I want to simplify the resistors. That's naturally what I want to do. There's only a single source here and a bunch of resistors. But then I start looking at these resistors and I realize none of them are in series and none of them are in parallel right now. So I had mentioned briefly once in class that there's these things called Y delta transformations, where you could take a constellation of resistors like this and turn it into a triangle instead. And if we did that, then we would start being able to have resistors in series and parallel. And there's a formula to relate each of these resistances to the ones over here on this circuit. This is called Y delta transformations, if you wanted to look that up in your textbook. But we didn't formally learn that in this class. So using the techniques you know, you'd actually have to apply the node voltage method in this case. Okay, I'll see you later. Bye.